Okay, I've had a cup of my tea and I'm all ready to tell you all about Edge serial connection for the ESP8266. My name is Rob Miles, www.robmiles.com, Twitter @RobMiles, and GitHub, for reasons that I'd rather not go into in too much detail, Crazy Rob Miles. Okay, so what am I talking about here? Um, well, quick word about edge-triggered software serial, what serial data is, how to use edge-triggered serial drivers to improve performance, and how to use my edge-triggered serial drivers. So this might be boring for you. In that case, just whiz past to the bit at the end that tells you how to make it work. But if you want to know how serial data works as well, this is all good stuff. So lots of devices that we talk to use serial data. GPS devices, air quality receiver, sensors, modems, all kinds of stuff. And serial data, as the name implies, is sent one bit, one episode, if you like, at a time down a single wire. It's cheap to use. Only one pin, only one wire, and it's been around since the very start of computing. I was using serial data when I was much younger and even handsomer, although I think I'm matured with age, than I am now. Okay, so as far as a data port is concerned, it doesn't really talk about numbers. It talks about things as high and low. A line can either be at a high state, which usually has a voltage on there of I don't know, about 5 volts or 12 or whatever, or a low state. What the data means when it's received, it depends on the program receiving it. We often talk in terms of serial data as being text data. This isn't always the case, but we do have a bunch of standards that map numbers onto character codes. ASCII, or UTF-8 as it's also called, map particular numbers in the range 0 to whatever onto particular characters. And I happen to know the letter A has the value 65. And you'll never guess what the value of letter B is. All right, I'll tell you, it's 66, and so on. So we have this convention. We want to we have this mapping of numeric values onto text, okay? And so let's say we want to send the value A, letter A, value 65, over a serial connection, okay? The hardware is going to send a bunch of pulses, not a number, and we need to have a protocol which actually lets us convert these pulses into a numeric value. And what we do is we say that a pulse in a particular position represents whether or not the number, the value we're sending, contains that particular power of 2. And we can represent any number in this way. It's the basis of how binary data works. And so take our 65, it's quite an easy one because we have to have a 64, which is 2 to the power 7, and a 1, which is 2 to the power 0. So we take those two bits and we go, okay, if we send those 2 bits as data bits and all the other bits as 0, we're sending the value 65. If that seems a bit confusing, stay with me. I'm hoping the next page will make things a little bit clearer. Here's my pattern of bits. There we go, at the top there. There's the first bit, that's the 1. Then no 2s, no 4s, no 8s, no 16s, no 32s, a 64, and no 128s. By convention, serial data is sent over 8 data bits. There might be other bits called parity and whatnot, but they're beyond the scope of this particular talk. So we have this idea here that we've got 8 data bits, and that bit there is set high to mean this value contains a 1, and that bit there is set high to say this value contains a 64, and you add them together and hey, you get 65. Note that all the pulses are the same width and the sender and the receiver agree on this width. This width is called, the time it takes each bit is called the baud rate. And baud stands for binary asynchronous unit of data. I know that because I'm very old. And if you think about how many bits we have in our packet, you can divide the baud rate by 10 to figure out how many characters per second are going to be coming down the wire, near enough. And so 9600 baud, which is the speed that most GPS receivers and other devices work at, works out at about, divide that by 100, that's about 960 characters per second. The receiver and the transmitter agree on the baud rate to use, but there's no clock signal. That's what asynchronous means. They're not synchronized. So both of them have an idea of how long that time is. And it doesn't matter if one of the clocks is a bit different. If the receiver's a little bit faster than the transmitter, it doesn't matter because the start bit at the beginning of every single data byte that's sent resynchronizes things. And the bottom bullet point, as you might expect, the higher the baud rate, the faster we send the data, so the more we can pack in. And what I'm talking about for my stuff only really becomes significant when you get to what we call really slow data rates these days, of things like 9600 baud and slower. If you're into this, you'll know what that means. If you are into this, you now have a useful fact you can bring out at the kind of dinner parties that you go to, as we all do. So in terms of my diagram, I'm going to show that the data traveling from right to left. So I've got a receiver on the left-hand side of my page, and this data is going into the receiver. The big arrow tells us that. Now, this might be a bit counterintuitive in terms of how we read stuff going the other way, but that's because of the way that these diagrams tend to be drawn from the point of view of a thing called an oscilloscope, which is what we use to look at the signals. So this bit here is the start of the signal, and then these are the bits chug along into my receiver. So this is how things are at the start, and what happens is my receiver's sitting there twiddling his digital thumbs and not doing much, and suddenly the start bit arrives, and that's signaled by the line dropping from the high level to the low level, and the receiver goes, aha, I've got some data coming. So I'll start building it up as it arrives on this wire. So the start bit falling edge is the trigger to mean, hey, I got your data for something to read, you see. So that's all jolly good. So what happens is the receiver sits down, it waits for a little while until it knows the first bit is now arriving. And sorry, the initial bit, not the first bit. First means 1 and it isn't, it's bit 0, which is confusing, but there you go. So the receiver knows how long it takes for a bit to arrive because it knows the baud rate. So it waits for a while, and then it wakes up and goes, okay, I'll sample you here, and you're high, so I'll call you a 1. And that's the initial data bit. We then wait a bit longer and sample again. And so now we're sampling data, the next data bit. This data bit, how many 2's there are in our number, if you like, is at the value low, at the level low. So it goes, okay, that's a 0. And it keeps on doing this. It wakes up here and here and here and here and here and here. And that should say D8. That is wrong. That should be a 6. That should be a 7. Oh, I am so sorry, but I'm not going to fix it just now because life's too short. So it's D5, D6, D7. That should be a 6. Oh, Robert, you are rubbish. Anyway, keep on going. And then finally D7 arrives. That's also low. So we now have this sequence here. That's the number of 1, 2, 8s. That's the number of 64s, 32s, 16s, 8s, 2s, 8s, 4s, and 2s and 1s, making my magical value of 65. This is how it works. The receiver now goes, I've got some data, and it will cause a thing called an interrupt that tells the processor, hey, come and look at me, I've got some data for you. And the processor will then go off and fetch that 8-bit value and then do something with it. And that depends on what your program wants to do with it. So that's how it works. This is a very important part, though. After the data has all come through, we have a thing called a stop bit, which is right at the very, very, very end of the data. And this is always high, and it's always 1 bit width, and it marks the end of the data. It assures the data line's nice and high at the end of a character, so the falling edge of the line, when it goes down here, that's the start bit of the next one. So the stop bit, very important, must be there, and it's how we keep things, the stop bit and the start bit, keep things synchronized. If another data byte is following immediately, of course what will happen is that line will drop straight away for the next start bit, and dum, away we go. Or alternatively, it might be a long time before the next byte arrives, so it might stay high for quite a while. Either way, the stop bit is guaranteed to be there, and it's guaranteed to give us a lump of high data state on the line that we can then use to sort of get ourselves relaxed and back together how we were. So we now know how serial data works. Yay, go us! So this is normally done in hardware by a little component that contains a clock and a counter and other bits and pieces, which will sample the incoming data for us, and they also do transmit as well. Transmitting is not what I'm concerned about here, because the things I'm talking to just send me data. I never talk to them. So it's called a universal asynchronous receiver transmitter. It's called a UART for short, and these things are built into the hardware, and that they just happen, and your program runs, and when bytes arrive, it gets told by the UART, hey, got some data, and we all move on from there. That's fine, but Sometimes you want to talk to more devices than you have hardware serial ports. Boo! At this point, you can always resort to a software serial port, which does the same thing, but uses the processor to do the timing and collecting of the bits. This is fine. You can use this as a software serial library on the ESP8266, which works wonderfully. And you can use you can have 4 or 5 of these if you want, but there are problems when you use very slow data rates, because if you look at my data signal, there's that D6 that should be D7 that's wrong, but I apologize for that, never mind. The way it works is it sees the falling start bit and it goes, okie dokie, I'm going to read a byte now. So it stops doing anything else and it samples the data here, 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 and you're going down the thing, builds the byte up, and then sends it on into the program. But for the duration that this is happening, your program is stopped. So your foreground program isn't doing anything at that point. Now this can be a problem because if you have a thing like a GPS receiver, these things send data pretty much continuously. They just spew out NEMA streams which you can then use to make sense of. Fine. But what that means is that for big chunks of time your program is stopped and only gets to run in these bits in the middle. So that can really slow. I've been doing animations on pixels while receiving serial data, and my animations stutter and slow down, and they're not as good. And that's because of the fact my program is effectively being stuck at regular intervals because incoming data is not is being received, and it's not allowing my program to run, which is sad face. So what we do is we look at how interrupts work. We go, okay, now the way that a software serial that you get with your Arduino tends to work is that at the falling edge, the processor goes, okay, I'm going to stop and I'm going to do all this measuring, and that's fine. Your program stopped there. That's the trigger. What I do for my routine is I have triggers every time we see a change in the state of the data line. And because I know when the data started to arrive, I can then work out from when these guys happen what these bits are. Now, it's not rocket science, it's just a bit fiddly. But it does mean that in all these times here, once my interrupt handler's finished doing the thing for that particular bit, the program keeps running. So that means that my main program is not interrupted and slowed and stopped for the entire data byte, just at these points. And that's quite nice. It means my programs run a lot faster and everything's a lot smoother. It's good because it gives another improvement too, which is that with the original software serial, if 2 characters arrive from different sources on different pins at pretty much exactly the same time, one of them might get missed because while the driver is reading one of the bytes, it can't respond to the other one. Now, the nice thing about this one is, my edge one, is that that doesn't happen. You can get things on 2 separate ports at exactly the same time and it will work a treat. And so it's great. The slower your baud rate, the better this works. It's just a complete reverse of how normal serial data is. But there is a problem, which I need to tell you about because it's important. Sometimes you see this byte here is sending 254, which is all these values except for D0. So we get our leading interrupt there, start bit, another interrupt there going back up, and then nothing. So my driver has no way of knowing the character is finished. Now, what that means is that this version, I don't know the character has arrived until something else down the line here triggers me. Now, that might be a problem for some applications. It's not a problem for things like the NEMA stream or the air quality sensors because they send continuously, and so it'll just keep itself sort of broadly up to date. But if you want to talk to a user like via a terminal, then this can be a problem. So do bear that in mind. If you want to use my library, you can find it on GitHub at ESP8266 Edge Software Serial on Crazy Rob Miles. Just add software serial .h and .cpp into your Arduino sketch folder and then include them using double quotes rather than less than greater than to mean use the local ones please, and you'll get the behavior of these nice shiny ones. The behavior is just the same, and the way you actually select edge triggered is that you use the same constructor you'd normally use, but this one here makes me a GPS serial port which will listen on pin 12. It will not transmit at all because I never want to tell the GPS receiver anything at all. It says we're not inverting our inputs. That's what false here means. Use a 128 byte character buffer for the input, and edge triggered operation please is what this final true means. If you leave it off, then you get exactly the same serial port behavior as you would normally get. Turn it on by putting true, and suddenly we're using edge triggered. And so that's how you flip between the two. Have a play, see if it makes your life better. I really hope it does. It's improved mine. So there you go. Yeah, thanks for watching. robmiles.com is the place to go for all the really good stuff, and Twitter at robmiles, or follow me on YouTube. Who knows what I might do next. But anyway, thank you for that. Hope it's useful.